In this video, we're going to prove 8 algebraic identities that are associated with complex numbers. Actually, to keep the videos short, I believe I'll just do 2 each, so we'll have 4 short videos. In this first video, I'm going to prove the first 2 algebraic identities, namely that the real part of a complex number z is equal to z plus its complex conjugate divided by 2. Let's start with that one. And for all of these, we will assume the following. We will assume that z can be written as x plus iy. So x is the real part of z, y is the imaginary part of z, and also on some of the future videos, we're going to need multiple complex numbers. So z1 we'll say is x1 plus iy1, and z2 is x2 plus iy2. Okay, that's just a way of breaking it down that makes proving these possible. Okay, well, let's start with the first one. And by the way, what is the real part of z? We've already said that. It's going to be x. So what I'm going to do is start with this right-hand side and show that it is equal to x. So z plus the complex conjugate of z all over 2 is equal to x plus iy, that's z, plus the complex conjugate of z is x minus iy, all over 2. Now let's simplify that. X plus x, that's 2x. Iy plus negative iy, well, they cancel each other out and we get 0, all over 2. We get x, which is the real part of z, as we expected. It's real. Okay, now let's do number 2. Number 2 says that the imaginary part of z is equal to this expression. Well, we already know what the imaginary part of z is. The imaginary part will be just the real number y. So I'm going to start with this right-hand side and simplify it and verify that I get y, which is equal to this. So z minus z bar, complex conjugate, over 2i. That's what we're starting with. That says z minus z bar. Well, that is equal to x plus iy, that's z, minus the complex conjugate of z, so you need the parentheses, x minus iy, all over 2i. Let's simplify the numerator. X minus x is 0. Iy minus negative iy is iy plus iy. That would give me 2 iy's. And the denominator is 2i. So the 2i cancels, leaving us with y, which is indeed the imaginary part of z. So we've proven 1 and 2, and in subsequent videos we will prove identities 3 through 8.